Let's look at this chain rule for a two-variable function with a single independent variable substitute. But let's look at it differently than can you just copy a formula or memorize a formula. If we were to just investigate these statements here, among the applications we learned in the earlier part of calculus when we were studying single variable everything, we might consider something like this, something like that. It might be considered, well, lots of things. I mean, it's a derivative, but we could call it a rate or a rate of change or an instantaneous rate of change. There are a number of meanings. But let's just think of it as some sort of a rate, and in this case t equals time. It doesn't have to be, but it's convenient for the applications, and I don't think it's an accident that our book writes it that way at all. In most books that are written in English will use this notation. It's not an accident. So let me show you why the chain rule is rather significant. The problem we're about to do needs this. It's not an option. Okay, so here it is. Let me just sort of keep details together here. All right, so let's say we have a triangle and the base is increasing at 0.2 centimeters per minute or 2 millimeters per minute. That could be written, that phrase alone, the base is increasing at that speed, that could be written as dB dt is a positive 0.2 centimeters per minute. You see, that's a rate. Okay, that's a rate. And then right here it says that the height is changing also, so dh dt, but the height is decreasing. Decreasing means it's getting smaller. We'll put a negative to represent that, 0.1 centimeters per minute. So we're never actually going to have what b is equal to and what h is equal to as a function. You're going to find out we're just not going to have a function. What we're going to have is, so we won't know what these are here. What we're going to have are these two values right there. So there is no substitution at the beginning of the problem. There's only using our chain rule to do this. So now for the question, which of course you've read because you're tired of listening to me. How fast is the area changing? Okay, so first of all, let's get a little visual here. Let's make a triangle. I don't want it to look like an isosceles triangle because it doesn't have to be. So we have a base and we have a height, if that's an altitude that's drawn correctly, and we would have that the area is equal to 1/2 the base times the height. Well, there we go. There are two variables here, but time is the one independent variable that's consistent in the whole problem. That's our single independent variable. It's independent of this. So according to this, the question actually is how fast is the area changing? And what that can be translated as is, what is dA dt? Well, according to our chain rule formula, I will take there's two variables here, so I'll do a partial derivative with respect to b and a partial derivative with respect to h, and then this would be times dB dt plus, and this will be times dH dt, if I'm correctly copying this formula down, but using, look, there's no x and y. It's almost not an algebra class anymore. We're like this close to the real world. All right, let's evaluate this now. So I'm going to break a rule of science here. My apologies and no offense intended. I'm going to include my units of measurement at the end, but keep them out of the substitution here at the beginning, just to save space and to emphasize the calculus part of this problem. So let's do this then. dA dt, which means the rate the area is changing. Okay, the rate that the area is changing. So if b is the variable here, the derivative of b is 1. That leaves you with 1/2 h left over. And we know that dB dt is 0.2. And again, there's units, centimeters per minute. The h partial derivative, the derivative of h would be 1, leaving you 1/2 b, and then dH dt is negative 0.1 centimeters per minute. I'm closing in on a numerical solution here. I'm getting close. Finally, I'm going to allow myself to read the rest of the question, which says, how fast is the area changing at the very moment in time when the base is 8 and the height is 5? Okay? Until you take your derivatives, you can't plug in those numerical values. Those values are changing. It says they're changing. So that means they have to stay a variable until after you do the calculus. So we've got our derivatives here. Now let's plug in what we have. We have 1/2 h is 5, 0.2, 1/2 base is 8, and negative 0.1. Let's see what we get here. Half of that's 0.1. This is going to be 0.5 or 0.5 when I'm finished. Half of 8 is 4. For those minus 0.4, I get 0.1 something. So what are the units? Well, I should have had centimeters here and here, and I should have had centimeters per minute here and here. I think you will find that you end up with centimeters squared per minute. Now, what does it all mean? Well, it means if the base is increasing and the height is decreasing, that the area is increasing at 0.1 square centimeters per minute. That's what it means. If we allow this story to continue, eventually the height is going to shrink down to nothing. But we use the chain rule to fill in the given information to actually find a measured rate. Stay tuned, we'll try another example.